This session will discuss about Kripkes model. So it is an extension of a proportional logic. So what is proportional logic? We'll be having some set of declarative statement, and a declarative statement are something like which just have an yes or no solution. And we have a set of connectives, and based on the connectives will like and or like implies and all, like we'll be connecting these statements, and we are going to find a solution for it. We are going to validate the statement as whether true or false. So that is your proportional logic. So in this session, in this video, we're going to discuss about Kripkes model. Like I just take an example first. Just when I write this statement, the sum of 2 plus 2 is 4. So when I assign a variable p, and that is going to take this value as the sum of 2 plus 2 is 4. So what does the statement actually means? 2 plus 2 is 4, right? It is going to be true whenever we take this p. Whenever we validate the statement, p is going to take the value as true always. Okay. Similarly, I just take one more statement. There are 9 planets in solar system. So I just assign the statement to Q. Now consider the statement. As of now, it is true. Q is true as of now. The thing is, like, there is no proven evidence, right? Like there may have, maybe you may have another planet too, but as of now, it is discovered that there are 9 planets in the solar system. And sometimes in the future, there is a possibility of finding a new planet too, right? So this is as per the current situation, it is true. In future, it may vary. So what about the representation for these kind of statements? So proportional logic statement actually deals with when the statement just is always going to be true or false. Okay, it is not going to describe about the future content, or it is not going to be described like when I say the sum of a place or some place, something like that, or varying in nature. So to represent all those kind of statements, we're going for this Kripkes model. So Kripkes model actually deals with certain concepts. Okay, it is going to focus on certain concepts, like either it might be a knowledge or time or necessity or something. So we're going to define Kripkes model over certain world, and in that world, we're going to find the relationship. Okay, so in order to represent these kind of things, like there are two more, like with all those proportional logic alphabets, we are going to introduce two more alphabet. One is this square, another one is this diamond shape. This square actually, it is a kind of similar to that of for all quantifier. It is a kind similar to it. It is not the same. Okay, when you see this predicate logic, we have used a quantifier for all, right? It is a kind of similar kind of structure for it. And this diamond shape actually represents for some. In the word, if for certain criteria, if this satisfies, then we can use this diamond shape. And square shape is for all criteria, if the given formula works, then we can use this square shape. Okay, so these two additional unary operators are added along with the existing operators of your proportional logic. So this is your unary operator. What does a unary operator actually means? It is going to deal with, like, again write it as P or diamond Q. I cannot write it as, so this is not LF. Like your negation, it actually applies with a single proposition variable. Okay, so this is all about your Kripkes model. Now I'll just give some the alphabets or the way in which a formula can be written in your Kripkes model. Like I just use the same Backus normal form structure. So all the formulas are similar to that of your proportional logic. So I'll be having either true or false or a single proposition, or we can write it as negation of a formula. And what all the connectives we have? Conjunction, disjunction, implies, bidirectional connective. And along with that, the present unary operator. So for any formula, we can attach it with this square shape or this diamond shape. Okay, so all this pi represents a formula. So this is how it is actually represented. This is your Backus normal form structure. So I can write any formula like this. P implies Q implies negation P. So this kind of formulas can be written. And this is a valid set of formulas. You can represent, like we can have any formula, and if it is actually satisfying these criteria, you can say it as either it is a valid or invalid kind of structure. So like it is a structure oriented. I'm not validating the formula as it is. Okay, validating in the sense like in a world we can verify it, but I'm just saying the structural representation. Is it possible to write a formula like this? No. See, when I am just going to represent your square shape, it has to be followed with a proposition, not like this. A proposition followed by this, a proposition followed by this, or connecting two propositions using these quantifiers is not allowed. These are all your invalid propositions. And this is a valid way of writing your Backus normal form for Kripkes model. So I'll show you the representation. See, whenever there is a formula, you should know the way in which it can be represented, validated. Okay, so validation in the sense, the priorities. The priorities are actually again similar to that of your propositional logic, predicate logic statement. So the highest priority actually goes with these two, and then you have your negation, and then you have your conjunction disjunction implies bidirectional condition. So when you are drawing a parse tree, you have to follow the sequence. Okay. So now for this statement, let me just draw a parse tree structure for it. So first, what I have to do, I have to do it for the one that is there in the brackets, and then over here. Okay, over here. So first it is P connected using a negation. Follow the sequence here. Connected using your diamond shape. Now your implies Q. This is your unary operator. Unary operator means it just have a single branch. Okay, so done for all this, and using your implies, I'm just going to connect it with P. Okay, so this is how we are going to represent a parse tree structure for your Kripkes model. Okay, so next one is semantical. Like we have to prove, like we know the way in which it is represented, right? We know what is in Kripkes model and some examples. The alphabets and the way in which a formula can be written, and the way in which it has to be validated, the way in which it has to be, a parse tree can be drawn. So what is next? To check the semantic entitlement of it, to check whether, like how we are going to validate any formula in this Kripkes model. So that is your next structure. So we can call that as a model. A model in a Kripkes model. Like usually what happens in case of your model in a propositional logic statement, we are going to find the interpretation, right? We'll be assigning true or false for any of the statement, and we're going to verify whether, see, for any interpretation of the formula, if you're able to derive to true, then we are going to say that this is a valid statement. This is your normal predicate propositional logic statement. But for your Kripkes model, a model is represented with three elements. So the three elements are like any model in Kripkes model is represented using a world. Okay, the current scenario, the world in which it is represented, along with the relationship settled with that corresponding world, and the labeling functions. So these three are the important way in which, three elements in which a model can be represented in Kripke. Kripke is the one who invented it. So his name actually followed over here. So now I'll just like, we can write it as, consider in this case, like if X is a formula, is a variable or an element in this W, and phi is the formula, we can write the statement as entitled to true. This is allowed. This is your semantic entitlement. It is going to verify whether X is present in the world or not. If X is present, it is true. If X is not present, it is false. Okay, and we can have a statement like this. When I write a statement like this, if in case for that X, like if this P is present in the language of, or in the label of your L of X, then it is allowed. Okay, similarly, we can write the statement for all your rules. Like when I just write the statement, semantic entitlement for negation pi, if X is not in this pi, then we can give it as pi is valid. Okay, and similarly, when I just write the statement as pi and psi, so this is possible only if X semantically entitled phi and X semantically entitled psi. If both satisfy, we can write this as the formula. Okay, so very important thing over here to know is regarding the new operators that we have used over here. That is, if we write it as X semantically entails this, it means that if for each Y that is belonging to this W, okay, in the world, all your W that are belonging with a relationship as X comma Y, we have Y entitled to psi. That is, let us just take one simple example to understand this criteria. Like I take this as my word. Okay, I have P here, P comma Q here. I have a relationship like this. Okay, so now this is your label. Your world actually consists of X and X2, and your relationship actually says that you have a relationship. I'm sorry. Okay, the world actually consists of X1, X2, and the relationship actually are there as X1, comma X2. We have a relationship between X1 and X2 defined. Okay, the transition is available. So when you write it as Q, this actually means that for all the Y, or Y in the sense all the world, okay, for all the words that are in the relationship between X1, just I give it as X1. So the word that are connected with X1 is X2. For all this, okay, if this Q is present in the labeling factor, then you can write it as this. This is valid. Okay, so this means that in X1, X1 is connected to X2. So there is a relationship exists. And in that relationship, you have this Q labeled. Yeah, the Q labeling is done. In case if I have one more relationship defined over here with the X3 without any labeling factor, I cannot write this. Okay, it is invalid. The reason is the word that is connected with this is like X3 doesn't have this Q. Okay, in that case, we cannot write like this. Okay, and the last statement to be defined is when I write it as diamond of psi, if there is a Y belonging to the world such that R of X comma Y and Y is in the world of that psi. Okay, if at least one satisfied, your formula actually satisfies over here. Okay, to understand this better, I'll take one example as a whole. I'll just define a model, define the relationship, and define the labeling factor. Then we can check the formulas, validate some formulas too. Okay, so let us consider the model. Consider this model M as WRL. So here W is represented as X1, X2, X3, X4, X5 and X6. Okay, and the relationship can be defined as, like, I just give the transition diagram here, that will do. Okay, relationship, instead of writing it, if I mention it like this, it will do. So here X1, this is for X2. I have a self loop here. I have a connection here. This is X3. I have this X4, X5, X6. Okay, so this is my model. In this model, we are going to take few of the formulas. Like here, X1 is labeled with Q. So all your relationship, W is all the word that consists of X1, X2, X3, X4, X5, X6. R is the relationship. You have a relationship between X1, X2, 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 and all these transition diagrams. And L is the labeling function. For X1, you have Q. For X2, you have P comma Q. For X3, we have P. Okay, one real-time example you can take it over here is like when I am just going to visit some kind of place. Okay, like X1 is the place where I am starting, and only one person Q is along with me. And next I'm going to reach X2 where P is going to join. And while moving to X3, Q is like he landed off, and we just have P alone inside. Okay, so this is like at certain world, at certain situations who are all there in the particular vehicle or something like this. You can consider an example like this. So world consists of all the element, and only few at each certain criteria, only few are there. So let us take some formulas and verify the validity of it. Like first formula, I'm just taking it as Q. What does that mean? In X1, do we have Q? Yes, right? Like Q actually belongs to the labeling element of X1. It is allowed. So this is present. So it means that it is a valid formula. Okay. So now when I just write it as with diamond of Q, what does that mean? For all the relationship that are connected with X1, so X1 is connected to, from X1 to X2, we have a relationship, and X1 to X3, we have a relationship, and this is there is at least one. Okay, if at least one, if it consists of Q, you can write like this. If it consists of Q, then it is allowed. So R of X1 to X2. In X2, do you have Q? Yeah, it is there. Okay. In X3, we don't have Q. This is not satisfied, but at least one criteria, if it is satisfying, then it is a valid formula. Okay. And similarly, when I write it as box of Q, is it valid? No, right? That is not valid. Like here in all the relationship that are combined with X1. Okay. So the world that are connected with X1 is X2 and X3. In X2, we have Q, but in X3, we don't have Q. So this is not valid. Okay, when a semantic entitlement is not valid, we can cross it like this. Okay, so one more example I can take as verify whether this is satisfied or not. What is P or Q? So X5 is connected to X4 and X6. So we are going to verify this X4 and X6. And it consists of either P or Q. So here you have Q and here we have P. So all the states either have either P or Q. So this is an valid formula. So this is how we validate a formula in your Kripkes model. Thank you.